The old man kneels on the cold marble floor of Santa Maria sopra Minerva, his joints protesting every movement. He is 69 years old. He is blind in one eye. He has been interrogated 4 times in as many weeks. The Grand Inquisitor stands above him holding a document. Galileo Galilei, once the most celebrated natural philosopher in Europe, once mathematician to the Grand Duke of Tuscany, once the man who showed Jupiter had moons and the sun had spots, reads from the paper in a voice that cracks. I abjure, curse, and detest the error and heresy of the movement of the earth. The words hang in the incense-thickened air of the Roman tribunal. Outside it is June 1633. The 30 Years' War is tearing Europe apart. Pope Urban VIII, who was once his friend, who once praised his work, has turned against him. The charge is holding and teaching as true a doctrine which is false and contrary to the sacred and divine scriptures, that the sun is the center of the universe and immovable, that the earth is not the center and moves. But Galileo has seen the moons of Jupiter cross the face of their planet. He has watched Venus display phases like the moon, proving it circles the sun. He has observed sunspots moving across the solar surface, demonstrating the sun rotates. He has mapped mountains on the moon, shattering the ancient belief in celestial perfection. His eyes have shown him truths that his mouth must now deny. This is not a story about a scientist versus the church. This is a story about a man who believed truth could be separated from power. Evidence from authority, observation from doctrine. He was wrong. And that wrongness cost him everything. But before we continue into that reckoning, I want to ask you something. If this story is moving you, if you're curious where it leads, take just a moment to like this video and subscribe to the channel. It helps more than you know. And I'm genuinely curious, where in the world are you watching from? Drop a comment below. I love knowing who's on this journey with me. Now let's go back to before the trial, before the telescopes, before the discoveries, back to where the question was born that Galileo would spend his life trying to answer. The question was this: if your eyes show you one thing and authority tells you another, which do you believe? Galileo di Vincenzo Bonaiuti de Galilei was born on February 15th, 1564, in Pisa. The city was already ancient, its famous leaning tower already tilting, its university already centuries old. But Pisa was declining. The silting of the Arno River had cut it off from maritime trade. It existed now as an intellectual outpost of the Medici dynasty, which ruled Florence and most of Tuscany. The Pisa of Galileo's birth was a city caught between past glory and present decline. The streets still held echoes of its maritime power. The Piazza dei Miracoli, with its cathedral and baptistery, spoke of wealth accumulated when Pisan ships dominated Mediterranean trade routes. But now the harbour was silting up, merchant families were moving away, and what remained was a university town where ideas circulated more freely than gold. In this environment between fading grandeur and intellectual ferment, Galileo's mind would first awaken to the world. Galileo's family was noble in name only. They descended from a prominent Florentine ancestor, Galileo Bonaiuti, who had served as a magistrate. But by the time of Galileo's birth, the family had fallen far. His father, Vincenzo Galilei, was a professional musician and music theorist, not a courtly composer writing masses for princes, but a working musician who taught lute and performed for money. Vincenzo was brilliant in his own right. He conducted experiments on string tension and pitch, physically testing musical relationships that theorists had taken on faith from Pythagoras. He published treatises challenging the established harmonic ratios, proving through measurement that the ancients had been wrong about the mathematics of consonants. Vincenzo's experiments were radical in their own way. He would stretch strings of equal length but different materials, gut, bronze, copper, and demonstrate that the traditional Pythagorean ratios did not hold universally. He hung weights from strings and measured how tension affected pitch. He documented his findings with meticulous care, showing that what the ancient authorities said about music was demonstrably incorrect. In the evenings, when young Galileo watched his father at work, he was witnessing something profound: the systematic dismantling of received wisdom through careful observation and measurement. This was not merely music theory, this was a method, a way of asking questions, a refusal to accept authority when your own hands could test the claim. This was the inheritance, not wealth, but method, not certainty, but questions, not deference to the old books, but the willingness to test them. Galileo's mother, Julia Ammannati, remains a shadowy figure. The sources describe her temperament as difficult, but say little more. We know she bore 7 children, 6 of whom survived infancy. We know Galileo, as the eldest son, would become responsible for them all. We know that financial anxiety would shadow his entire life because of it. When Galileo was 10, the family moved to Florence. It was 1574. The Counter-Reformation was in full force. The Council of Trent had concluded just 11 years earlier, codifying Catholic doctrine in explicit opposition to Protestant Reformation. The Church was asserting its authority over every domain: theological, political, philosophical, scientific. This was the air Galileo breathed. Florence in the 1570s was a city of contradictions. The Medici court patronized art and learning, yet the Inquisition maintained offices there. Scholars debated Aristotle in the universities, while heretics were occasionally tried and punished. It was possible to pursue knowledge, but only within carefully defined boundaries. The question of where those boundaries lay and who had the authority to define them was never entirely clear. This ambiguity created space for inquiry, but it also created danger. A scholar could spend years working on a problem only to discover too late that he had crossed an invisible line. His early education took place at a Camaldolese monastery at Vallombrosa, southeast of Florence. The order emphasized study and contemplation. Galileo excelled. He nearly became a novice monk himself, but Vincenzo, his father, withdrew him. Whether this was about Galileo's potential religious vocation or about Vincenzo's need for his son to pursue a lucrative profession, the sources do not say. Probably both. In 1581, at 17, Galileo enrolled at the University of Pisa to study medicine. This was the expected path. Medicine was respectable, well-paid, and practical. The Galilei family needed money. They needed Galileo to become someone who could support his sister's dowries and sustain the household after Vincenzo's death. Medicine would do that. Mathematics would not. But then came the deviation, the moment that split his life in two. In 1583, Galileo attended a mathematics lecture by Ostilio Ricci, a court mathematician to the Grand Duke. Ricci was teaching the mathematical works of Euclid. Galileo had never encountered geometry before. Medicine required memorizing Galen and Hippocrates, understanding humors and temperaments, mastering materia medica. Mathematics required proof. It required demonstration. It required that you show why something was true, not merely that authorities said it was true. The lecture hall was modest, attended by a handful of students and courtiers who needed practical mathematics for military engineering and fortification design. Ricci was explaining Euclid's proof that there are infinitely many prime numbers. Galileo, who had wandered in out of curiosity, found himself transfixed. The proof was elegant, inevitable. You assumed there were only finitely many primes, then constructed a number that could not be divided by any of them, thus proving your assumption wrong. It was a form of reasoning unlike anything in his medical studies. It did not appeal to Galen's authority or Hippocrates' experience. It simply showed you why the conclusion must be true. Galileo felt something click into place in his mind. This was what he had been looking for, without knowing he was looking for it. Galileo was transfixed. He began attending Ricci's lectures without his father's knowledge. He studied Euclid in secret. Then Archimedes. Archimedes had used geometry to calculate the volumes of irregular shapes, the buoyancy of objects in water, the mechanical advantage of levers and screws. Archimedes had shown that mathematics could describe the physical world, could predict how things would behave. This was different from medicine, different from philosophy, different from theology. Mathematics did not care what Aristotle said. It did not care what Scripture said. It was true because you could prove it was true. Vincenzo discovered what his son was doing and was furious. Mathematics was useless. Mathematicians were poorly paid tutors. They had no prestige, no security. Galileo was throwing away his future. The arguments between father and son grew bitter. But Galileo would not relent. He had found something that satisfied a need he had not known he possessed. He left the University of Pisa in 1585 without a degree, having abandoned medicine entirely. The next 4 years are poorly documented. Galileo was in his early 20s, living with his family in Florence, with no profession, no income, and no clear path forward. He gave private mathematics lessons. He wrote a small treatise on the hydrostatic balance, describing a method for determining the specific gravity of objects. He called it La Bilancetta, the little balance. It was clever but minor. It earned him a small reputation among Tuscan mathematicians, nothing more. These were years of uncertainty and frustration. Galileo was living in his father's house, dependent on family support, watching his former medical school classmates establish practices and build reputations while he taught geometry to merchants' sons for a few scudi per lesson. His siblings looked at him with a mixture of pity and resentment. His mother openly criticized his choices. Only Vincenzo, despite his initial anger, seemed to recognize something in his son's obsession. Perhaps he saw echoes of his own battles with musical orthodoxy. Perhaps he simply understood what it meant to pursue an idea when the world told you to be practical. But Vincenzo could not protect Galileo from financial reality, and financial reality was unforgiving. Then, in 1589, the University of Pisa appointed him to the chair of mathematics. He was 25 years old. The position paid 60 florins per year. For comparison, the chair of philosophy paid 500. Mathematics was a marginal discipline, but it was a foothold. 2 years later, his father died. Vincenzo had been 54. Galileo became the head of the household at 27. He was now responsible for his mother, his siblings, and the debts his father had left behind. His sisters needed dowries. Each dowry would cost hundreds of florins. He was earning 60. This pressure would drive every decision he made for the next 2 decades. It would push him to seek patrons, to pursue fame, to accept positions that placed him in dangerous proximity to power. It would lead him, eventually, to the Inquisition. But first, it led him to Padua. In 1592, the University of Padua offered Galileo the chair of mathematics at 180 florins per year, triple his Pisan salary. Padua was in the Republic of Venice, beyond the immediate reach of Rome. Venice jealously guarded its independence from papal authority. Venetian scholars enjoyed intellectual freedom unavailable elsewhere in Italy. Galileo accepted. The 18 years he spent in Padua from age 28 to 46 were the freest and most productive of his life. He taught geometry and astronomy. He studied motion, mechanics, and the behavior of falling bodies. He designed a military compass for gunners and sold them on the side for extra income. He lived openly with a woman named Marina Gamba, though they never married. She bore him 3 children, 2 daughters and a son. Padua gave Galileo something he had never had before: space to think. The teaching load was manageable, the intellectual climate was open, and the Venetian Republic's defiance of papal authority created a bubble of relative freedom. He rented a house large enough to accommodate students who boarded with him, which supplemented his income. He set up a workshop where he built mathematical instruments, compasses, calculating devices, demonstration apparatus. Marina Gamba managed the household, raised the children, and tolerated his obsessive focus on his work. The arrangement was not conventional, but it was stable. For nearly 2 decades, Galileo had what every scholar dreams of: time, autonomy, and intellectual community. His circle of friends and correspondents expanded. He exchanged letters with mathematicians across Europe. He debated with colleagues over dinner, testing ideas, working through problems. He taught the sons of Venetian patricians, which brought in extra fees and established connections that would prove valuable later. He was not yet famous, but he was respected. He was not yet wealthy, but he was solvent. He was not yet in danger because he had not yet challenged anything that mattered to those in power. The Padua years were formative in ways that went beyond his scientific work. It was here that Galileo learned to navigate the complex social world of patronage and reputation. He understood that discoveries meant nothing if no one knew about them, that arguments needed an audience, that intellectual authority had to be carefully cultivated and defended. He learned to write letters that flattered without seeming obsequious, to demonstrate his instruments in ways that impressed potential patrons, to frame his work in terms that mattered to those who held power. These were not skills taught in universities. They were the survival skills of the early modern intellectual, and Galileo mastered them during these years of relative obscurity in Padua. Why did Galileo never marry Marina? We do not know. The sources are silent. He came from minor nobility, and she did not, which may have mattered. Or he may have wished to avoid the legal entanglements of marriage and inheritance. Or he may simply not have loved her enough to make it binding. We do know that when he left Padua in 1610, Marina did not come with him. We know he placed his daughters in a convent when they were barely teenagers. Virginia was 13, Livia 12. He called them illegitimate and claimed convents were the only appropriate place for them. The dowries would have been cheaper that way too. This is not the Galileo of legend, the pure hero of science. This is a man caught between ambition and obligation who sometimes chose ambition. But in Padua he was not yet forced to make those choices so starkly. He was teaching, experimenting, thinking. He was part of an intellectual circle that included Paolo Sarpi, a Venetian friar and scholar who was studying optics and the nature of light. It was Sarpi who would later help Galileo understand the instrument that would change everything. Then came 1600. In February of that year in Rome, the Dominican friar Giordano Bruno was burned alive in the Campo dei Fiori. Bruno had argued that the universe was infinite, that stars were distant suns, that other worlds existed beyond Earth. He had denied the Trinity, rejected transubstantiation, mocked church authority. The Inquisition had tried him for 8 years before deciding his heresies were unrecantable. They tied him to a stake, gagged him so he could not speak, and lit the fire. The news reached Venice slowly, carried by travelers and merchants. When Galileo heard of Bruno's execution, he was 36 years old, comfortable in Padua, focused on problems of motion and mechanics. Bruno's death was a shock, but perhaps not a surprise. Everyone knew Bruno had been in prison. Everyone knew he had refused to recant. But the finality of it, the actual burning, the reduction of a human being to ash for holding ideas, that concentrated the mind. Galileo knew scholars who had known Bruno. He had read some of Bruno's cosmological speculations. He did not agree with all of them, and he certainly did not share Bruno's theological heresies. But the boundary between natural philosophy and heresy suddenly seemed very thin. In the weeks after Bruno's execution, Galileo found himself more cautious in his public statements. He had been teaching Copernican astronomy as a mathematical hypothesis, showing how it simplified calculations without asserting it as physical truth. Now even that seemed potentially dangerous. Bruno had not been burned for astronomy alone. His heresies were theological, but his cosmological ideas had been part of the case against him. Galileo began to understand something that would shape the rest of his life. The content of your ideas mattered less than the context in which you presented them, and the context was determined by forces beyond your control. You could say something safely one year, and the same statement could destroy you the next, not because the statement had changed, but because the political weather had shifted. The message was clear. There were limits to speculation. There were truths the Church would defend with execution. Galileo was 36 years old. His first daughter had just been born. He was teaching mathematics in Padua, working on motion and mechanics, not yet touching astronomy or cosmology. But the warning was there. Bruno had not been killed for astronomy. He had been killed for denying doctrine. But he had denied doctrine partly on cosmological grounds. The boundary between natural philosophy and heresy was not clear, and the Church was willing to burn those who crossed it. Then, 9 years later, in 1609, word reached Italy of a device invented in the Netherlands. It was made of 2 lenses mounted in a tube. Looking through it made distant objects appear closer. The Dutch called it a spyglass. Some said Hans Lippershey had invented it. Others said Zacharias Janssen. There was a dispute over priority. What mattered was that it worked. Galileo heard about the spyglass and immediately grasped its implications. If you could make distant objects visible, you could change warfare. You could see enemy ships before they saw you. You could see troop movements from miles away. Venice, a maritime power, would pay for such an instrument. But Galileo also grasped something else. If you could magnify distant objects on Earth, you could magnify distant objects in the sky. And if you could do that, you could see things no human had ever seen. You could test cosmological theories by looking at the heavens directly, rather than merely reasoning about them. He obtained lenses. He ground better ones. He experimented with different focal lengths and apertures. Within months, he had built a telescope that magnified 9 times, then 20 times, then 30 times. This was not invention. The Dutch had invented it. But Galileo had perfected it, and he had understood what to do with it. In 1609 and early 1610, Galileo turned his telescope to the night sky. And what he saw shattered the Aristotelian cosmos. First, he observed the moon. Aristotle had taught that celestial bodies were perfect spheres, unchanging and unblemished, made of a different substance than the corrupt sublunary world. But through Galileo's telescope, the moon was revealed to be rough, mountainous, cratered. It looked like Earth. Galileo calculated the height of the lunar mountains by measuring the length of their shadows. They were miles high. The heavens were not perfect. They were material, physical, subject to the same laws as earthly matter. Then he turned the telescope to Jupiter. On January 7th, 1610, he noticed 3 small stars near the planet, arranged in a straight line. He thought they were background stars. The next night they had moved. He watched for weeks. The number of stars varied, sometimes 3, sometimes 4. They appeared and disappeared as they moved behind or in front of Jupiter. They were not stars at all. They were moons orbiting Jupiter. This was devastating to the Ptolemaic Aristotelian system. If moons could orbit Jupiter, then not everything in the cosmos orbited Earth. The Earth was not the unique center of all motion. There could be multiple centers. And if Jupiter could have moons, then the Copernican model, which placed the Sun at the center and had Earth and planets orbiting it, became geometrically plausible in a way it had not been before. Galileo observed the Milky Way and discovered it was not a nebulous glow but countless individual stars, too faint to see with the naked eye. The revelation was staggering. On clear nights in Padua, Galileo would point his telescope at different regions of the Milky Way, sketching what he saw, trying to capture the sheer density of stars that the instrument revealed. Where the naked eye saw a hazy band of light, the telescope showed star fields so crowded they defied counting. If the universe contained so many stars invisible to ordinary sight, what else might be hidden? What other secrets awaited discovery? The telescope had not just extended human vision, it had exposed the profound limitations of what humans had assumed they could know. He observed Venus and saw that it displayed phases like the moon, sometimes a full disk, sometimes a crescent. This proved Venus orbited the Sun, not Earth. In the Ptolemaic system, Venus should never show a full phase as seen from Earth, because it should always be between Earth and the Sun. But Galileo saw it full, which meant it sometimes passed behind the Sun. Only the Copernican arrangement explained that. He compiled his observations into a short book, Sidereus Nuncius, the Starry Messenger. It was published in Venice in March 1610, just weeks after his Jupiter moon discoveries. It caused a sensation across Europe. Astronomers rushed to build their own telescopes. Some confirmed his observations, others claimed they saw nothing or accused him of trickery. The Aristotelian philosophers, whose entire worldview depended on celestial perfection and Earth's centrality, attacked him viciously. But Galileo was famous. He was celebrated. Cosimo II de' Medici, the Grand Duke of Tuscany, who had been Galileo's mathematics pupil years earlier, appointed him court mathematician and philosopher. The salary was 1,000 florins per year, more than 10 times what Pisa had paid, with no teaching duties. Galileo could pursue research full-time, so in 1610, at age 46, Galileo left Padua. He left Venice, with its intellectual freedom and its distance from Rome. He moved to Florence, into the heart of Medici power, into the jurisdiction of the Roman Inquisition. He left Marina Gamba behind. He took his daughters and placed them in the convent of San Matteo in Arcetri, outside Florence. Virginia, the elder daughter, took the name Sister Maria Celeste. She would become the person Galileo loved most, the one whose letters would sustain him in his final years, the one whose death would break him. Why did Galileo leave the safety of Padua? Money, certainly. The Medici salary solved his financial problems, but also ambition. He wanted to be at the center of power, close to Rome, where his work would have maximum impact. He believed his discoveries proved the truth of the Copernican system, and he believed the Church could be persuaded to accept that truth. He thought evidence would be enough. This was his fatal miscalculation. He believed in a world where observation trumped authority, where what you could demonstrate with instruments and mathematics would override what ancient texts said. He was wrong. Power does not care about evidence unless evidence serves power. In 1613, Galileo published letters on sunspots. He had observed dark spots on the surface of the sun, which moved across the solar disk and then disappeared, only to reappear on the opposite side days later. The spots proved the sun rotated. They also proved the sun was not unblemished, not perfect, not immutable. Aristotle had been wrong about the sun, just as he had been wrong about the moon. But more dangerously, in the letters on sunspots, Galileo explicitly endorsed the Copernican system for the first time in print. He argued that his telescopic observations made the sun-centered cosmos not merely mathematically convenient, as Copernicus had cautiously framed it, but physically true. The Earth moved. The Earth orbited the sun. This was not hypothesis, this was fact. The attacks began immediately. Lodovico delle Colombe, a Florentine philosopher, organized a group he called the Colombe, the Doves, to oppose Galileo. They wrote letters to church authorities pointing out that Galileo's claims contradicted Scripture. Joshua 10:13 said the sun stood still, not the earth. Ecclesiastes 1:5 said, the sun rises and sets, implying it moves. If the earth moved and the sun stood still, then Scripture was wrong, and if Scripture was wrong, then the entire edifice of church authority crumbled. Galileo tried to argue that Scripture spoke in the common language of appearances, not in the technical language of natural philosophy. When Scripture said the sun rises, it meant the sun appears to rise, just as we still say today, not that the sun literally moves. The truth of physical motion was a separate domain from the truth of salvation. God had given humans two books, the book of Scripture and the book of nature. Both were true, but they spoke different languages. If they appeared to conflict, the fault was in our interpretation, not in God. This argument had theological sophistication. Augustine had made similar arguments 12 centuries earlier, but it required the Church to cede authority over the natural world to natural philosophers. It required the Church to admit its traditional readings of Scripture could be wrong. In 1613, in the midst of the Counter-Reformation, with Protestant reformers questioning every aspect of church tradition, the Church was not interested in ceding anything. In December 1615, a Dominican friar named Niccolò Lorini forwarded one of Galileo's private letters on Scripture and science to the Inquisition in Rome. The Inquisition opened a file. Consultants were asked to evaluate the Copernican propositions. In February 1616, they reported, the idea that the sun is at the center and immobile was declared formally heretical because it contradicted Scripture. The idea that the earth moves was declared erroneous in faith. On February 25, 1616, Cardinal Roberto Bellarmine, the Church's leading theologian, and the man who had prosecuted Giordano Bruno, summoned Galileo. What was said in that meeting is one of the critical mysteries of Galileo's life. We know Bellarmine admonished Galileo not to hold or defend the Copernican doctrine. We know Galileo agreed. We know Bellarmine gave him a letter certifying that Galileo had not been tried or penanced, but merely informed of the decree against Copernicus. But there is another document in the Inquisition file, an unsigned, unwitnessed injunction that claims Galileo was ordered not to hold, defend, or teach Copernicanism in any way whatever, verbally or in writing. This is far stronger language than Bellarmine's admonition. If the injunction was real, Galileo was essentially silenced. If it was not real, if it was added to the file later by enemies or by bureaucratic error, then Galileo had room to maneuver. Galileo left that meeting believing he could still discuss Copernicanism hypothetically, as long as he did not advocate it as true. Bellarmine's letter seemed to support that reading. For the next 16 years, that ambiguity would protect him, and then it would destroy him. The meeting with Bellarmine had been cordial, even friendly. Bellarmine was no ignorant inquisitor. He was one of the most sophisticated theologians in Europe, a man who understood philosophical nuance, who had read Galileo's work with genuine interest. But he was also the man who had sent Giordano Bruno to the stake. He understood the limits of what the Church could tolerate, and he understood that those limits were not determined by reason or evidence, but by institutional necessity. He warned Galileo not out of personal animus, but out of genuine concern. He was telling Galileo, "This is as far as you can go, do not go further." Galileo heard the warning. He thought he could navigate around it. He was wrong. In 1616, the Church placed Copernicus's De Revolutionibus Orbium Coelestium on the index of prohibited books pending corrections. The corrections were minor, just enough to frame the heliocentric system as mathematical hypothesis rather than physical truth. Galileo's own works were not banned. He was still the celebrated mathematician to the Grand Duke. He was still respected. He had been warned, but not condemned. He retreated from public controversy. He worked on other problems. He studied comets and tides. He argued with Jesuit astronomers about the interpretation of telescopic observations. He wrote a book on scientific method called Il Saggiatore, the Assayer, which was published in 1623. It contained one of the most famous passages in the history of science. Philosophy is written in this grand book, the universe, which stands continually open to our gaze. But the book cannot be understood unless one first learns to comprehend the language and read the letters in which it is composed. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures without which it is humanly impossible to understand a single word of it. This was Galileo's creed. Nature was mathematical. Understanding nature required mathematics, not scripture, not Aristotle, not tradition. Just observation and calculation. The years between 1616 and 1632 were years of strategic silence and careful maneuvering. Galileo continued his research, but he published cautiously. He corresponded with scholars across Europe, sharing ideas privately that he dared not print publicly. He cultivated relationships with powerful churchmen, building alliances he hoped would protect him when the time came to speak openly again. He watched the political landscape shift, waiting for an opening. The comet debates of 1618 to 1623 consumed much of his energy during this period. Several bright comets appeared, and their nature became a matter of fierce dispute. The Jesuit astronomer Orazio Grassi argued that comets were celestial objects beyond the moon's sphere, moving through the heavens. Galileo, writing under a student's name and then openly in the Assayer, argued that comets were optical phenomena in the upper atmosphere, not solid bodies at all. He was wrong about this. Comets are indeed celestial bodies, but the debate gave him an opportunity to articulate his views on scientific method without directly challenging the Copernican ban. The Assayer was a masterpiece of rhetoric and polemic. Galileo demolished Grassi's arguments with withering precision, mocking his reliance on Aristotelian categories and scholastic reasoning. He insisted that nature spoke in mathematics, not in the syllogisms of philosophy. He defended the primacy of observation and measurement over textual authority. The book was celebrated and, crucially, it was dedicated to Cardinal Maffeo Barberini, who had been a friend and supporter of Galileo for years. The Assayer was dedicated to Cardinal Maffeo Barberini, who had been a friend and supporter of Galileo for years. And in 1623, Maffeo Barberini became Pope Urban VIII. Galileo believed this was his moment. His friend was now the most powerful man in the Church. Urban VIII had praised the Assayer. Surely now Galileo could complete the project he had been forced to abandon in 1616. He could write the full argument for the Copernican system, showing how all the observations made sense in a sun-centered cosmos and made no sense in an earth-centered one. He could demonstrate the truth and vindicate himself. He sought and received permission from the Pope to write a book comparing the two world systems, Ptolemaic and Copernican, as long as it treated Copernicanism hypothetically and presented both sides fairly. The book would be reviewed by church censors before publication. Galileo agreed to these terms. He spent the next 6 years writing the Dialogo sopra I due massimi sistemi del mondo, the dialogue concerning the two chief world systems. It was structured as a conversation among 3 characters over 4 days. Salviati represented the Copernican view. Simplicio represented the Aristotelian Ptolemaic view. Sagredo was the neutral, intelligent layman who asked questions and weighed the arguments. The writing of the dialogue consumed Galileo utterly. He worked through illness, through family crises, through the distractions of court life. He revised constantly, trying to strike the right balance between making his arguments forcefully and maintaining the appearance of neutrality. He knew he was walking a tightrope. He knew the book would be scrutinized by hostile readers looking for any hint of heresy. But he believed he could make the case for Copernicanism so compellingly, so rationally, that even skeptics would have to acknowledge the evidence. The dialogue was a masterpiece of scientific exposition and rhetorical persuasion. It walked through every major objection to the Earth's motion and refuted them. It explained why we do not feel the Earth moving, why objects dropped from towers fall straight down even though the Earth rotates beneath them, why birds and clouds are not left behind as the Earth speeds through space. It presented the telescopic discoveries and showed how naturally they fit into the Copernican framework. It discussed the tides and argued, incorrectly, that the tides were caused by the sloshing of water due to the Earth's motion, providing direct mechanical proof of that motion. But the book was not neutral. Salviati, the Copernican, won every argument. Simplicio was made to look foolish, clinging to outdated ideas, unable to counter the evidence. And in the final pages, Simplicio repeated an argument that Pope Urban VIII himself had made to Galileo, that God, being omnipotent, could cause the tides or any other phenomenon by infinite possible means, so we could never be certain of the true cause. This was theologically sound. It was also the weakest argument in the book, presented at the moment of Salviati's rhetorical triumph. It looked like mockery. Whether Galileo intended to insult the Pope is unknown. Perhaps he genuinely thought he was honoring Urban's argument by including it. Perhaps he was so convinced of his own correctness that he did not see how it would read. Perhaps he had enemies who pointed out the insult to the Pope and inflamed his anger. We do know that Simplicio was a traditional name for Aristotelian characters in dialogues, not an invention of Galileo's. We also know that the Pope took it personally. The dialogue was published in Florence in February 1632, after navigating the censorship process. It sold out immediately. It was celebrated across Europe, and within months, the Pope ordered it banned and Galileo summoned to Rome. What happened? The book had been approved by the censors. It had treated Copernicanism hypothetically, as instructed. But someone, perhaps Scheiner the Jesuit astronomer, whom Galileo had humiliated in the sunspot debates, perhaps one of the Aristotelian philosophers, presented the unsigned injunction from 1616 to the Pope. The injunction said Galileo was forbidden to teach Copernicanism in any way. The dialogue clearly taught it. Therefore, Galileo had violated a direct order of the Inquisition. He was to be tried. Galileo was 68 years old. He was ill. Florence was under quarantine due to plague. He begged to be allowed to answer charges in writing or to be tried in Florence. The Inquisition refused. In January 1633, he travelled to Rome, staying with the Tuscan ambassador to the Vatican. The journey to Rome was arduous. Galileo travelled by litter, too weak to ride a horse. The quarantine measures meant long delays at borders, inspections, forced isolations. What should have taken a week stretched to nearly a month. He arrived in Rome in February, exhausted and frightened. The Tuscan ambassador, Francesco Niccolini, provided him with comfortable apartments, but Galileo knew he was effectively a prisoner. He could not leave. He could not publish. He could not defend himself publicly. He could only wait for the Inquisition to summon him and hope his explanations would be believed. The waiting was agonizing. Weeks passed. Galileo knew the charges against him, but not what evidence had been presented, not who had testified, not what verdict was being prepared. He wrote to friends, to former students, to anyone who might intercede on his behalf. Some responded with sympathy but could do nothing. Others did not respond at all, not wanting to be associated with a man accused of heresy. Galileo felt the isolation closing in. He had been one of the most celebrated intellectuals in Europe. Now he was alone, facing an institution that had burned men for less than what he had done. He was interrogated in April. The questions focused on the 1616 injunction. Had he been ordered not to teach Copernicanism? He produced Bellamine's certificate, which did not mention teaching. The inquisitors showed him the injunction. He claimed not to remember such an absolute prohibition. He insisted he had written the dialogue in good faith, believing Bellamine's terms allowed hypothetical discussion. He was interrogated again, then threatened with torture if he did not confess. He was old, sick, and terrified. On June 22, 1633, he confessed. He admitted that in rereading the dialogue, he saw that he had made the Copernican arguments too strong, that he had not maintained proper neutrality. He had been vainglorious, too pleased with his own cleverness. He had sinned through pride. He would recant. The confession was devastating to write. Galileo's hand shook as he signed the document. He was admitting that the work of his life, the observations he had made, the conclusions he had drawn from them, were errors born of vanity. He was saying that his eyes had lied to him, or that he had lied about what his eyes had seen. He was accepting that authority was stronger than evidence, that power was stronger than truth. He was betraying everything he believed in. But the alternative was torture, possibly death, and he was too old and too broken to be a martyr. The sentence was delivered the same day. The dialogue was banned. Galileo was to recant formally, abjuring the heliocentric heresy. He was sentenced to indefinite imprisonment at the pleasure of the Inquisition, later commuted to house arrest. He knelt in the Dominican convent of Santa Maria sopra Minerva and read the abjuration. I abjure, curse, and detest the error and heresy of the movement of the earth. He was not tortured. The Inquisition records are clear. He was threatened with torture, but it was not carried out. This matters because the myth that Galileo was tortured became part of the anti-clerical narrative of the Enlightenment. He was not tortured. He was humiliated, silenced, and imprisoned. That was enough. After the sentencing, he was allowed to return to his villa in Arcetri outside Florence. He would spend the remaining 8 years of his life there, forbidden to leave, forbidden to publish, forbidden to receive visitors without permission. His daughter, Virginia, Sister Maria Celeste, was in the convent a short walk away. He wrote to her constantly. She wrote back. Her letters are full of warmth, concern for his health, small domestic details. They kept him sane. Virginia's letters from this period are heartbreaking to read. She worried constantly about her father's health, his state of mind, his ability to cope with confinement. She sent him small gifts, pastries she had baked, herbal remedies for his ailments, copies of prayers she thought might comfort him. She asked about his work, not because she understood it, but because she knew it mattered to him. She never reproached him for placing her in the convent, never complained about her own circumscribed life. She simply loved him with a generosity and selflessness that Galileo had rarely shown to anyone. Her letters were a lifeline, the one source of uncomplicated affection in a world that had turned hostile. Then, in April 1634, just 10 months after the trial, Virginia died. She was 33 years old. The cause is not recorded, perhaps illness, perhaps the strain of witnessing her father's destruction. Galileo was devastated. He wrote to a friend, "I feel immense sadness and melancholy, together with extreme inappetite. I am hateful to myself, and continually hear calls from my beloved daughter." The grief was compounded by guilt. Galileo knew that he had placed Virginia in the convent not out of concern for her welfare, but out of financial expedience. He had given her a life of enclosure and deprivation, and she had responded with nothing but love. Now she was gone, and he could not even attend her burial. The Inquisition had not given him permission to leave Arcetri. He mourned alone in his villa, surrounded by books and instruments that no longer brought him joy. He was 70 years old, blind in one eye, confined to his house, forbidden to work, and now without the person he loved most. It would have been understandable if he had given up. He did not. Instead, he returned to the work he had abandoned decades earlier. The work on motion, on falling bodies, on the mathematical laws governing acceleration and force. The work that did not touch cosmology or theology, that could not be accused of contradicting Scripture. He compiled his notes from Padua, his experiments with inclined planes and pendulums, his theorems about projectile motion and the strength of materials. He wrote a new book, Discorsi e dimostrazioni matematiche intorno a due nuove scienze, discourses and mathematical demonstrations relating to two new sciences. The two new sciences were kinematics, the study of motion, and the study of the strength of materials and structures. The book laid the mathematical foundations for classical mechanics. It introduced the concept of uniform acceleration, proving that in free fall, velocity increases proportionally with time, and distance increases proportionally with the square of time. It analyzed the parabolic trajectory of projectiles. It discussed the breaking strength of beams and the limits of scaling in structures, explaining why you cannot simply make an animal larger and expect its bones to support the increased weight. The structure of two new sciences was deliberately cautious. Galileo framed it as a dialogue like his earlier work, but he avoided cosmology entirely. There was no mention of Copernicus, no discussion of whether Earth moved. The focus was purely on terrestrial mechanics, falling bodies, projectiles, materials, science. These were problems that could not be construed as heretical. No scriptural passage addressed the tensile strength of beams or the acceleration of falling weights. Galileo had learned his lesson. If he could not speak freely about the heavens, he would speak about the earth, and in doing so, he would lay the foundation for a new physics more radical than anything in the dialogue, even if the Inquisition never understood that. This was the work that Newton would build on. This was the foundation of physics as a mathematical science. And Galileo wrote it in his 70s under house arrest after being forced to recant his life's work. He could not publish it in Italy. The Inquisition would never allow it, but he could smuggle the manuscript out. The Protestant Netherlands, beyond papal reach, was printing scientific works. In 1638, Two New Sciences was published in Leiden by Lodewijk Elsevier. Galileo's students, Evangelista Torricelli and Vincenzo Viviani, helped with the final preparations. Galileo was 74. By the time the book appeared, he was completely blind. The blindness came gradually, then suddenly. First, the one eye which had been damaged years earlier, perhaps from looking at the sun through the telescope. Then the other, which began to fail in 1637. By 1638 he could no longer read, could no longer observe, could no longer see the faces of the few visitors who came to Arcetri. He dictated letters to his students, describing the darkness closing in. The irony was not lost on him. He had spent his life looking, seeing things no one had seen before, and now he could see nothing. The progression of blindness was torturous to witness, according to Viviani's accounts. First, Galileo needed brighter light to read, then magnification, then reading became impossible except for short periods. He could still see shapes, movement, light and shadow. Then that too began to fade. He tried various remedies, poultices, bloodletting, prayers. Nothing helped. By the autumn of 1637, he was describing himself as having 1.5 eyes. By early 1638, he had none. The universe he had spent his life studying was now closed to him. The instruments he had perfected sat unused. The observations he might have made would never be made. He was entombed in darkness while his mind remained sharp, active, hungry for the data his eyes could no longer provide. He described his blindness in a letter. This universe, which with my remarkable observations and clear demonstrations I have enlarged 1,000 times beyond the size universally accepted by learned men of all centuries past, is now for me so diminished and reduced it has shrunk to the meagre confines occupied by my own body. He lived 4 more years. Torricelli and Viviani stayed with him, serving as assistants and scribes. He continued to think about problems in mechanics. He dictated letters. He received occasional visitors. The Grand Duke wanted to build a monument to him. The Pope forbade it. Galileo had died condemned. On January 8, 1642, at age 77, Galileo died at Arcetri. The cause was recorded as fever and heart palpitations, natural causes for a man his age. His body was buried quietly, without ceremony, in a side chapel of the Basilica of Santa Croce in Florence. It would be 95 years before his remains were moved to the main body of the church and given a proper monument. The immediate reaction to his death was muted. In Catholic lands he remained a controversial figure, a man who had defied the church and paid the price. In Protestant lands he became a martyr for truth against superstition. Both narratives were oversimplifications. Within a decade, his students had ensured his work survived. 2 new sciences circulated widely. Torricelli, who invented the barometer, built on Galileo's principles. In England, Isaac Newton read Galileo's work on motion and used it as the foundation for his Principia Mathematica. The Galilean-Newtonian synthesis became the framework for all of classical physics. By 1700, Galileo's physics had triumphed, even if his astronomy remained officially condemned. The transmission of Galileo's ideas across Europe was neither automatic nor inevitable. It required active work by dedicated individuals who recognized the importance of what he had done. His students copied manuscripts, corresponded with scholars in other countries, translated his Italian works into Latin so they could reach a wider audience. They defended his priority against rivals who tried to claim his discoveries. They taught his methods to the next generation. The scientific revolution that we see in retrospect as an inevitable march of progress was actually a fragile network of personal relationships, smuggled manuscripts, clandestine teachings, and gradual institutional change. Galileo's ideas survived because people chose to keep them alive, often at risk to themselves. In 1757, over a century after his death, the Church quietly removed the dialogue from the index of prohibited books. In 1835, the Church formally accepted heliocentrism. In 1992, Pope John Paul II acknowledged that the Church had erred in condemning Galileo, stating that theologians at the time had failed to grasp the autonomy of science. But these rehabilitations miss the deeper point. Galileo's tragedy was not that the Church was anti-science. Many churchmen supported him initially. Jesuits confirmed his telescopic observations. Cardinal Barberini praised his work before becoming Pope Urban VIII. The tragedy was that Galileo believed evidence could exist outside power, that truth could be separated from politics. He believed he could navigate the court, could maintain patronage, could argue his case and be vindicated by the sheer weight of observation and mathematics. He believed in a world where what you could prove mattered more than who you offended. He was wrong. The trial had almost nothing to do with astronomy and everything to do with authority. The Copernican question was settled for Galileo by 1613. He knew the Earth moved. The question was whether he could say so. And that question depended not on evidence but on power, alliances, patronage, and perception. When he lost the Pope's favour, when his enemies found the injunction that could be used against him, when the political situation made an example useful, the truth of heliocentrism became irrelevant. He was crushed not because his science was wrong, but because his politics were naive. Consider the paradox at the centre of Galileo's life. He argued for intellectual freedom while seeking the patronage of absolute rulers. He claimed to speak truth while depending on men who could silence him on a whim. He wanted to separate natural philosophy from theology while living in a world where the Church controlled universities, censored books, and could imprison or execute those who defied it. He wanted the authority to overturn Aristotle while insisting that authority did not matter, only evidence. This contradiction was not unique to Galileo. It is the contradiction of every intellectual who depends on power to amplify their work. The patron system that funded Galileo's research also constrained it. The same Medici court that gave him leisure to observe the heavens also made him vulnerable when political winds shifted. The same pope who praised the assayer destroyed him when the dialogue made Urban look foolish. And Galileo himself was no saint. He was vain, combative, and arrogant. He mocked his opponents savagely, turning intellectual disputes into personal vendettas. He claimed credit for discoveries made by others. He treated his family as obligations to be minimized. He placed his daughters in a convent because it was cheaper than providing dowries, then abandoned them to that life while he pursued fame. He had affairs but never married Marina Gamba, never gave his children legitimacy. When it suited him, he was ruthless. Why does this matter? Because the simplified narrative of Galileo, martyr of science, hero of reason, victim of religious obscurantism, erases the actual man. And in erasing the man, it erases the lesson. The lesson is not that science defeats superstition if we just wait long enough. The lesson is that truth is never enough on its own. Evidence does not argue itself. Instruments do not interpret themselves. Someone has to speak for the data, and how they speak, to whom they speak, with what alliances and with what enemies determines whether they are heard or silenced. Galileo spoke brilliantly, but he spoke without understanding the court he was in. He thought he was in a debate. He was in a trial. What did Galileo actually discover? What were the telescopic observations that made him famous? Start with the moon. Before Galileo turned his telescope to it in 1609, the moon was thought to be a perfect sphere, luminous and smooth, made of some crystalline or ethereal substance unlike earthly matter. Aristotle had decreed that celestial bodies were fundamentally different from terrestrial ones. The heavens were perfect, unchanging, incorruptible. The earth was imperfect, changing, subject to decay. This division was not casual, it was cosmologically necessary. It explained why the heavens moved in perfect circles while earthly motion was irregular and eventually stopped. But through the telescope, the moon was nothing like that. Its surface was rough, cratered, mountainous. The terminator, the line dividing day and night, was not smooth, but jagged. Bright points of light appeared on the dark side of the terminator, isolated from the main illuminated area. Galileo recognized these as mountain tops catching the sun before the light reached the valleys below, exactly as happens on Earth at sunrise or sunset. He measured the shadows and calculated the heights of the lunar mountains. Some were 4 miles high, comparable to the highest peaks on Earth. This observation destroyed the distinction between celestial and terrestrial. If the moon had mountains, it was made of the same kind of matter as Earth. If it was made of the same matter, there was no reason to think it followed different laws. The physics of the heavens and the physics of Earth were the same physics. Then Jupiter. On January 7th, 1610, Galileo noticed 3 small stars near Jupiter, arranged in a line. Over the following nights, he watched them move. By January 13th, he had seen a 4th. By January 15th, he understood what they were. They were moons, satellites of Jupiter, orbiting it just as our moon orbits Earth. This was theologically and cosmologically explosive. In the Ptolemaic Aristotelian model, everything revolved around Earth. Earth was the unique center of all motion. The existence of bodies that clearly orbited something other than Earth shattered this uniqueness. If Jupiter had moons, there was no reason Earth could not be one planet among many orbiting the Sun. Galileo named them the Medicean stars in honor of Cosimo de' Medici, the Grand Duke of Tuscany. This was not modesty. This was patronage. Galileo needed money, needed protection, needed a position that would free him from teaching duties. Naming the moons after the Medicis was a calculated move, and it worked. Cosimo appointed him court mathematician and philosopher within months. The moons of Jupiter also provided a solution to a practical problem that had stumped navigators for centuries, determining longitude at sea. Latitude could be measured by the altitude of the sun or stars, but longitude required knowing the time difference between your current location and a reference point. Galileo proposed using the orbits of Jupiter's moons as a cosmic clock, visible from anywhere on Earth. Observers could note when a moon entered or left Jupiter's shadow, and by comparing that time to tables of predicted eclipses, calculate their longitude. It was a brilliant idea. It was also impractical on a ship, where the rocking motion made it nearly impossible to keep a telescope trained on Jupiter for the minutes or hours necessary to observe an eclipse. The method worked on land, and surveyors did use it to improve maps, but it never solved the nautical problem. That would wait for the marine chronometer in the 18th century. But Galileo saw the potential profit in it. He negotiated with Spain, with Venice, with the Netherlands, trying to sell the method. He designed apparatus, wrote instruction manuals, trained observers. It consumed years of effort and earned him almost nothing. This is the Galileo rarely mentioned, not just the disinterested seeker of truth, but the man hustling for contracts, trying to monetize his discoveries, navigating early modern patronage and proto-capitalism. Next, the phases of Venus. In the Ptolemaic system, Venus was between the Earth and the Sun, always closer to us than the Sun was. This meant Venus should always appear as a crescent when viewed from Earth, because only the dark side or a sliver of the illuminated side would be visible. It should never appear more than half illuminated. But when Galileo observed Venus through the telescope in 1610 and 1611, he saw it go through a full set of phases from crescent to half to nearly full and back. This was only possible if Venus orbited the Sun, sometimes passing between Earth and Sun, sometimes passing behind the Sun. The Ptolemaic system could not account for it. The Copernican system predicted it exactly. This was not direct proof that Earth orbited the Sun. The Tychonic system proposed by Tycho Brahe, which had planets orbiting the Sun but the Sun orbiting Earth, also predicted the phases of Venus, but it eliminated the Ptolemaic system as a possibility, and it meant that at least some of the Copernican model was physically correct. Then, sunspots. In 1612, Galileo began observing dark spots on the surface of the Sun. This required looking at the Sun through the telescope, which he did by projecting its image onto a screen to avoid blindness. The spots appeared, moved across the solar disk and disappeared at the edge, only to reappear on the opposite edge days later. They demonstrated that the Sun rotated, completing a rotation roughly every month. More importantly, they showed the Sun was not perfect. Aristotle and the scholastic tradition held that the Sun, like all celestial bodies, was immaculate, without blemish or change. Sunspots proved this wrong. The heavens were dynamic, imperfect, material. If the Sun had spots, there was no reason to believe it was fundamentally different from Earth. The celestial-terrestrial divide collapsed further. Galileo became embroiled in a bitter dispute with the Jesuit astronomer Christoph Scheiner over who had discovered sunspots first. Multiple observers had reported them around the same time, but Galileo insisted on his priority. Scheiner, who was constrained by his order's reluctance to challenge Aristotelian doctrine, initially published anonymously and suggested the spots might be small planets passing in front of the Sun, rather than features on the Sun itself. Galileo mocked this interpretation and publicly claimed the discovery as his own. The dispute became personal. Scheiner was a talented astronomer and a proud man. Galileo's mockery stung. Years later, when Galileo was tried in 1633, Scheiner was in Rome, and some historians suspect he played a role in presenting evidence against Galileo. Patronage politics and personal vendettas intertwined constantly in Galileo's career. His scientific achievements cannot be separated from the social world in which he operated. Finally, the structure of the Milky Way. With the naked eye, the Milky Way appears as a diffuse band of light across the sky. Ancient theories suggested it was an atmospheric phenomenon, perhaps an exhalation from Earth. Through the telescope, Galileo saw that it resolved into countless individual stars, too faint to distinguish separately without magnification. The universe contained far more stars than anyone had imagined. If there were so many stars, perhaps Giordano Bruno had been right to suggest they were distant suns, that the universe was vast beyond comprehension. This was dangerous speculation. Bruno had been burned for it just 9 years earlier. Galileo did not push the idea, but the implication was there. If stars were distant suns, then perhaps they had planets. Perhaps those planets had life. Perhaps Earth was not unique, not special, not the sole focus of creation. The telescope had opened an abyss. These discoveries, compiled in Siderius Nuncius and subsequent works, made Galileo famous, but they also made him a target. Every observation challenged received authority. The moon's mountains challenged Aristotle. Jupiter's moons challenged the uniqueness of Earth. Venus's phases challenged Ptolemy. Sunspots challenged celestial perfection. The Milky Way suggested an infinite universe, which challenged the Christian cosmos of a finite creation with Earth at the center and heaven above. Galileo believed the observations spoke for themselves. He believed that once people saw what the telescope revealed, they would accept the new astronomy. He was wrong. The Aristotelian philosophers argued that the telescope distorted vision, that its images were artifacts of the lenses. The theologians argued that even if the observations were real, they did not prove what Galileo claimed. Alternative explanations were possible, and in any case, if observation contradicted Scripture, observation must be wrong because Scripture was divinely inspired and could not err. This was not stupidity or superstition. It was a coherent epistemological position. The Aristotelian scholastic tradition held that knowledge came from reason applied to self-evident first principles, not from the unreliable testimony of the senses. The senses could deceive. Only logic, applied correctly, yielded certainty. Galileo's empiricism inverted this. He claimed the senses extended by instruments were the foundation of knowledge, and reason must conform itself to what observation revealed. This conflict was not just about astronomy, it was about what counted as knowledge, who had the authority to determine truth, and whether the world was fundamentally rational and accessible to human inquiry, or fundamentally mysterious and knowable only through revelation. Galileo chose the former. The Church, at that moment in history, defending itself against Protestant reformers who questioned its authority to interpret Scripture, could not afford to choose the former, so it chose to silence Galileo instead. But Galileo's legacy was not primarily his telescopic discoveries, it was his method. It was the insistence that nature could be interrogated, that observation and experiment were superior to authority, that mathematics was the language in which nature spoke. This method would outlive the Inquisition. It would become the foundation of the scientific revolution. And it would transform the world far more profoundly than any single observation ever could. Let us return to motion. This was Galileo's first love, the problem he studied long before he turned his telescope to the sky. Aristotle taught that heavier objects fall faster than lighter ones. This seemed obvious. A stone falls faster than a feather. A large rock falls faster than a small pebble. The natural place of heavy objects was down toward the center of Earth, and the heavier the object, the more powerfully it sought its natural place. This had been accepted for nearly 2,000 years, but Galileo questioned it. The story everyone knows is that he dropped two objects of different weights from the Leaning Tower of Pisa and observed that they hit the ground at the same time. This story is almost certainly false. It appears first in a biography written by Galileo's student Vincenzo Viviani decades after Galileo's death, and no contemporary source mentions it. But the conclusion was correct. Objects of different weights do fall at the same rate, air resistance aside. How did Galileo demonstrate this? Through thought experiments and inclined plane experiments, not dramatic public demonstrations. The thought experiment went like this. Suppose Aristotle is right, and heavier objects fall faster. Take a heavy stone and a light stone and tie them together with a string. What happens when you drop them? According to Aristotle, the light stone should slow the heavy stone down because it falls more slowly, so the combination should fall slower than the heavy stone alone. But the combination is heavier than either stone alone, so it should fall faster than the heavy stone alone. This is a contradiction. The only way to resolve it is to admit that weight does not affect the rate of fall. This was pure reasoning, but reasoning from observation, not from first principles. It showed that the Aristotelian position contained an internal inconsistency, but it was not experimental proof. For that, Galileo used inclined planes. A ball dropped straight down falls too fast to measure its motion with the instruments available in the early 17th century. But a ball rolling down a shallow incline falls slowly enough that you can time its descent. Galileo constructed inclined planes with a groove down the center. He released bronze balls from rest at the top and timed how long they took to reach various points down the plane. He discovered that the distance traveled increased as the square of the time elapsed. If a ball took 1 second to travel a certain distance, it would travel 4 times that distance in 2 seconds, 9 times in 3 seconds, 16 times in 4 seconds. This was uniform acceleration. The velocity increased steadily proportional to time, and this relationship held regardless of the weight of the ball. This was revolutionary. Aristotle's physics had no concept of acceleration. In Aristotelian physics, objects moved at constant speeds determined by their nature and the medium through which they moved. But Galileo showed that falling was not constant motion but accelerating motion, governed by a mathematical law. He extended this to projectile motion. A cannonball, once fired, moves both forward and downward. Aristotle had struggled to explain projectile motion. How could something continue to move after the force propelling it had ceased? Aristotle suggested the air rushed in behind the projectile and pushed it forward, a theory that made little sense even to medieval commentators. Galileo showed that projectile motion was a combination of two independent motions: horizontal motion, which continued at constant velocity because nothing opposed it, and vertical motion, which accelerated downward due to gravity. The combination produced a parabolic trajectory. He calculated the equations describing this path and showed that the range of a projectile was maximized at a 45-degree launch angle. This work appeared in two new sciences published in 1638 when Galileo was 74 and blind. But he had been working on these problems for 50 years. They were the foundation of everything else. The telescope made him famous, but the mathematics of motion made him the father of physics. Why does motion matter? Because motion was the fundamental problem of natural philosophy. The cosmos was defined by motion. Planets moved in circles or epicycles depending on your system. The Earth either moved or stood still, and that question defined cosmology. Understanding motion meant understanding the structure of reality itself. Aristotle's physics could not account for the motion Galileo observed. It had no place for acceleration. It could not explain why projectiles followed parabolic paths. It could not explain why objects of different weights fell at the same rate. So Aristotle's physics had to be discarded, and with it went the entire edifice of scholastic natural philosophy that had been built on Aristotelian foundations. This is why the Church fought Galileo so hard. It was not really about whether Earth moved, it was about whether Aristotle could be wrong. Because if Aristotle could be wrong about motion, he could be wrong about the nature of the soul, about the structure of the cosmos, about the relationship between matter and form. And Aristotle was woven so deeply into Catholic theology through the work of Thomas Aquinas in the 13th century that challenging Aristotle threatened the entire intellectual structure of the faith. Galileo did not set out to destroy Catholic theology. He was a believing Catholic his entire life. He wanted the Church to see that Scripture and the new science were compatible, but he underestimated how much the Church had invested in Aristotelian philosophy as the framework for understanding revelation. You could not pull out Aristotelian physics without the whole structure threatening to collapse. And so the Church chose to defend Aristotle. It chose to silence Galileo. And in doing so, it ensured that when Aristotelian physics finally fell, as it inevitably did, the Church's authority would fall with it. The trial of 1633 was not a victory for the Church. It was the beginning of the end of its intellectual dominance over European thought. Newton read Galileo. He absorbed the principles of inertia, the mathematics of acceleration, the laws of falling bodies. He extended them into a universal law of gravitation, showing that the same force that made apples fall to Earth kept the moon in orbit and the planets circling the sun. The Principia Mathematica, published in 1687, 45 years after Galileo's death, completed what Galileo had begun. It showed that the heavens and the earth were governed by the same laws, that those laws were mathematical, and that human reason could discover them. This was the scientific revolution, and Galileo was its prophet, even if he did not live to see it triumph. What about the failures, the things Galileo got wrong? Start with the tides. Galileo was obsessed with the tides. He believed they were the proof of Earth's motion. If Earth moved, the oceans would slosh back and forth in their basins like water in a moving bucket. This sloshing would produce the daily tides. It was direct mechanical proof that Earth was moving. He was wrong. Tides are caused by the gravitational pull of the moon and, to a lesser extent, the sun. Newton explained this in the Principia. But Galileo rejected lunar influence on tides as astrological superstition. He mocked the idea that the moon could affect water from such a distance. His mechanical explanation was elegant, intuitive, and completely incorrect. This matters because it shows Galileo was not infallible. He was capable of clinging to wrong ideas for the same reason his opponents clung to Aristotle, because they fit his worldview, because they confirmed what he already believed. He wanted a mechanical proof of Earth's motion. He found a mechanism he thought worked. He defended it against criticism and ridicule. He was wrong. The tides argument took up a large portion of the dialogue, the book that got him tried. It may have been one reason the Pope was so offended. Galileo presented the tides argument as decisive, as unanswerable proof. Urban VIII, who was not a fool and who understood that certainty was elusive in natural philosophy, had cautioned Galileo against claiming too much. When Galileo ignored that caution and put Urban's cautionary argument in the mouth of Simplicio, the simpleton character, it looked like arrogance, like hubris, like mockery. It was, in part, all of those things. Galileo also failed to engage seriously with Kepler's work. Johannes Kepler, the German astronomer and mathematician, had published Astronomia Nova in 1609, the same year Galileo built his telescope. Kepler showed that planetary orbits were not circles or combinations of circles, but ellipses, with the Sun at one focus. He derived 3 laws of planetary motion that described the speeds and periods of the planets with extraordinary precision. Galileo read Kepler's work. He acknowledged Kepler's genius, but he never accepted elliptical orbits. He continued to believe that heavenly motion must be circular because circles were perfect and uniform. This was an aesthetic judgment, not a scientific one. It was the same kind of thinking he accused Aristotelians of using. Circles seemed right, seemed natural, seemed fitting. So circles must be correct. They were not. Kepler was right. And Galileo's refusal to accept ellipses was a failure of his own method. He should have followed the evidence. The evidence pointed to ellipses. He chose aesthetic preference instead. Similarly, Galileo never fully embraced the idea of universal gravitation, the notion that all objects attract all other objects with a force proportional to their masses and inversely proportional to the square of the distance between them. This idea was implicit in Kepler's work and would be made explicit by Newton. But Galileo seems to have thought of gravity as a specifically terrestrial phenomenon, pulling objects toward Earth's center. The idea that gravity might extend to the moon, to the planets, to the stars, that it might be a universal force structuring the cosmos, does not appear clearly in his work. This is partly because Galileo was focused on motion itself, not on the forces causing motion. He was doing kinematics, the description of motion, not dynamics, the explanation of motion in terms of forces. That distinction mattered less then than it does now. But it meant Galileo laid the groundwork for Newtonian mechanics without constructing the full framework himself. Another failure. Galileo did not develop a theory of light. He used lenses, he understood refraction well enough to build telescopes, but he never systematically investigated the nature of light itself. That work was done by others. Descartes, Huygens, Newton. Galileo had the experimental skill and mathematical ability to contribute, but he was consumed by the cosmological debates and the political battles. He spent years responding to critics, defending his priority in discoveries, courting patrons. The work that might have deepened our understanding of optics was never done. Was Galileo a great experimenter? Yes and no. He was brilliant at designing demonstrations and thought experiments that clarified principles. The inclined plane work was genuinely experimental, but much of what he described as experimentation was actually mathematical reasoning about idealized situations. He imagined perfect spheres rolling on frictionless planes in a vacuum. Real balls rolling on real wood introduce friction, air resistance, imperfections. Galileo was aware of these complications, but he argued that understanding the ideal case was necessary before addressing real-world messiness. This was a methodological innovation. It was the birth of mathematical physics. Abstract from messy reality to find the underlying law, then add back the complications as corrections. But it also meant that Galileo was not primarily an experimentalist in the modern sense. He was a mathematical theorist who used carefully chosen demonstrations to illustrate principles he had already worked out mathematically. Compare him to someone like Robert Hooke in the next generation, who was constantly building apparatus, testing materials, exploring phenomena empirically. Galileo was more abstract. He wanted the mathematical law. The phenomena were illustrations of the law, not the primary object of study. This difference in approach mattered enormously for the development of physics. Galileo was less interested in cataloguing the diversity of natural phenomena than in finding the universal principles underlying them. He believed that once you had the mathematical law, you could derive everything else. This was both his strength and his limitation. His strength because it led him to profound insights about motion and mechanics that pure empiricism might have missed. His limitation because he sometimes tried to force messy reality into mathematical frameworks that did not quite fit. The mature science that emerged in the following centuries would need both approaches: Galilean mathematical idealization and empirical attention to detail. But Galileo's contribution, the insistence that nature spoke in mathematics, was the more radical departure from the past and the more necessary foundation for what came after. None of this diminishes his achievement, but it makes him human. He had blind spots, he made mistakes, he held on to wrong ideas. He ignored evidence when it contradicted his aesthetic preferences. He was not the flawless hero of Enlightenment mythology. He was a brilliant, flawed man working without the luxury of hindsight, trying to construct a new way of understanding nature from fragments of observation and insight. And he succeeded, not completely, not without error, but he succeeded in shifting the ground under natural philosophy. After Galileo, you could not simply cite Aristotle. You had to show, you had to measure, you had to calculate. You had to make your claims precise enough to be tested. That shift was Galileo's true legacy. What was Galileo like as a person? What do the sources tell us about his character, his relationships, his inner life? He was vain. The sources are unanimous on this. He believed he was the smartest man in any room, and he usually was, but he made sure everyone knew it. His letters are full of sharp wit, clever arguments, cutting remarks about opponents. He did not suffer fools. He did not pretend to respect people he thought were stupid. This made him many enemies. He was also charming when he wanted to be. Contemporaries describe him as a brilliant conversationalist, witty, engaging, able to hold a dinner party wrapped with explanations of his discoveries. He could be warm, generous with students, patient with genuine questions. But that charm was strategic. He needed patrons, he needed allies, he needed people to defend him and promote his work. So he cultivated them. His relationship with his family is more troubling. He never married Marina Gamba, despite living with her for a decade and having 3 children with her. When he left Padua for Florence in 1610, he took the children, but left Marina behind. Why? The sources do not say. Perhaps he believed his position at the Medici court required him to be unencumbered by a partner of low social status. Perhaps the relationship had simply run its course. We do not know. What we do know is that he placed his 2 daughters in the convent of San Matteo in Arcetri when they were 13 and 12 years old. They took vows and spent the rest of their lives there. Galileo claimed this was because they were illegitimate and could not marry respectably. But it was also cheaper than providing dowries. Convents required smaller contributions than marriage dowries did. Galileo was supporting his siblings, paying off his father's debts, trying to maintain a lifestyle appropriate to a court mathematician. His daughters' futures were sacrificed to those pressures. Virginia, the elder daughter, who became Sister Maria Celeste, maintained a loving relationship with her father despite this. Her letters to him are full of affection, worry about his health, requests that he visit, small gifts sent back and forth. She seems to have genuinely cared for him. Whether she resented being placed in the convent, we cannot know. Her letters do not say. But the fact that she maintained the relationship suggests either genuine forgiveness or the complete internalization of a world where women's choices were made by their fathers and resistance was futile. Livia, the younger daughter, who became Sister Arcangela, was less reconciled. The fragmentary evidence suggests she was unhappy, ill-tempered, difficult. She blamed her father for her situation. Their relationship was strained. After Virginia died in 1634, Galileo had little contact with Livia. She was a reminder of guilt he did not want to face. His son, Vincenzo, was legitimized after Galileo achieved prominence. Galileo secured his recognition by the Grand Duke and arranged a marriage for him. Vincenzo inherited property and social position. The daughters inherited nothing but a convent cell. This double standard was typical of the era, but knowing it was typical does not make it less troubling. Galileo, who argued for the autonomy of reason and the authority of observation, who insisted that truth should not be subordinated to tradition, accepted without question the subordination of his daughters to economic and social convenience. Did he feel guilt about this? His letters after Virginia's death suggest he was devastated. He wrote that he felt immense sadness and melancholy, that he was hateful to himself, that he continually heard his daughter calling. Whether this was guilt or simply grief, we cannot know. But he spent the last 8 years of his life grieving a daughter he had confined to a convent at age 13. Galileo's financial anxieties shaped every major decision of his life. He left Padua for Florence because the Medici salary was 3 times what Padua paid. He courted patrons obsessively, dedicating works to them, flattering them, seeking their protection. He tried to monetize his discoveries, selling telescopes, negotiating with governments over the longitude method, seeking prizes and pensions. He was not above exaggerating the practical utility of his work if it meant securing funding. This does not make him a hypocrite. He needed the money. He had real obligations. His family depended on him. But it does mean his career cannot be understood purely in terms of disinterested pursuit of truth. He was navigating a patronage system where your ability to continue working depended on pleasing powerful men, and powerful men could be fickle, petty, and dangerous. The relationship with Pope Urban VIII illustrates this perfectly. Maffeo Barberini, before becoming Pope, was genuinely interested in science and mathematics. He admired Galileo. He praised the assayer. When he became Pope in 1623, Galileo believed he had a friend at the highest level of church authority. He sought and received permission to write about the Copernican system as long as he presented it hypothetically. But Urban was not just a patron of natural philosophy. He was the head of the Catholic Church in the midst of the 30 Years' War, facing Protestant challenges to papal authority, navigating complex political alliances under constant pressure to assert doctrinal orthodoxy. When Galileo published the Dialogue in 1632, and when Urban's enemies pointed out that the simpleton character Simplicio repeated the Pope's own argument, Urban felt humiliated, he felt betrayed, he felt Galileo had used their friendship as cover to mock him publicly. Was this paranoia? Was it an overreaction? Perhaps. But Urban was under immense political pressure. He could not afford to appear weak or foolish, and Galileo had, intentionally or not, made him look both. So Urban turned on him. The trial followed. Galileo seems not to have anticipated this. He genuinely seems to have believed Urban would protect him. This was a catastrophic failure of political judgment. It suggests that for all his brilliance, Galileo did not understand power. He thought intellectual argument mattered. He thought evidence mattered. He thought friendship mattered. In the world of Roman politics in 1633, none of those things mattered as much as perception, authority, and the Pope's need to demonstrate control. After the trial, after the recantation, after the sentence to house arrest, Galileo never fully recovered his confidence. His letters from the final years are subdued, resigned. He continued to work, completing 2 new sciences despite blindness and illness. But the fire was gone. He had learned that truth was not enough, and that lesson broke something in him. Yet he did not give up. He continued to think, to calculate, to dictate his ideas to students. The work on motion, on the strength of materials, on the mathematics of physical law, all came from those final years under house arrest. Perhaps work was all he had left. Perhaps it was defiance, quiet and private, where public defiance had failed. Perhaps it was simply who he was. The last years are painful to contemplate. An old man, blind, confined to his villa, forbidden to publish, forbidden to see most visitors, grieving his daughter, aware that his life's work had been condemned by the institution he had tried to serve. He died on January 8, 1642, with his students Viviani and Torricelli at his bedside. He was 77. The Grand Duke wanted to build a monument. The Pope forbade it. Galileo was buried quietly in a side chapel of Santa Croce. His enemies had won, or had they? Within a century, the Copernican system was accepted across Europe. Within 2 centuries, the Church had quietly removed his works from the index. Within 3.5 centuries, a Pope formally acknowledged the Church had erred. Within 4 centuries, the spacecraft that explored the outer solar system bore his name. The moons of Jupiter he discovered are called the Galilean satellites. The enemies who tried him are forgotten. The ideas they tried to suppress became the foundation of modern science. Galileo lost the battle, but he won the war. This is the standard conclusion of the Galileo story. Martyred by dogma, vindicated by history, truth crushed to earth shall rise again. The arc of the moral universe bending toward justice. But that conclusion is too simple. It erases the complexity of what actually happened. It makes Galileo a symbol rather than a man. It makes the Church a monolith rather than a collection of individuals with competing interests. It makes the scientific revolution inevitable rather than contingent. The truth is messier. Galileo was not purely right. The Church was not purely wrong. The conflict was not between science and religion, but between different claims to authority, different ways of knowing, different institutional interests, and the outcome was not inevitable. If Galileo had been more politically astute, he might have lived free. If Urban had been more secure, he might not have felt threatened. If the 30 Years' War had not been raging, the Pope might not have needed to assert orthodoxy so forcefully. History is not a morality play. It is a series of contingencies, accidents, personalities colliding, systems straining, ideas spreading in ways no one fully controls. Galileo's story is not a lesson in the triumph of reason. It is a lesson in the fragility of reason in the face of power. And yet, the ideas survived. The method survived. The insistence that nature could be read, that mathematics described the world, that observation trumped authority, all of that survived. Not because it was invincible, but because enough people, scattered across Europe, found it useful. Because it worked. Because it let them predict eclipses, build better cannons, understand motion, navigate seas, because it answered questions the old philosophy could not answer. Galileo did not single-handedly create the scientific revolution. He was one voice among many, but he was a loud voice, a clear voice, a voice that insisted we could trust our instruments and our mathematics more than we could trust ancient books. And that voice echoed. It echoes still. What does Galileo mean today? Why should someone in the 21st century care about a 17th century astronomer who was tried for heresy and died under house arrest? Start with the method. Galileo did not invent the scientific method, but he practiced it and advocated for it more clearly than perhaps anyone before him. The insistence that observations must be recorded carefully, that experiments must be repeatable, that mathematics must describe natural phenomena, that theories must make predictions that can be tested, all of that is now so fundamental to science that we barely notice it. But it was not obvious in 1600, it was revolutionary. And Galileo embodied it. Every time a scientist publishes data, every time an engineer tests a prototype, every time a medical researcher runs a clinical trial, they are operating in the tradition Galileo helped establish. The idea that evidence matters, that you can be wrong, that you should check, that you should measure, that you should calculate, all of that descends from the transformation Galileo was part of. But more than the method, Galileo represents a permanent question. What do you do when what you can see contradicts what you are told to believe? This is not just a question about astronomy, it is a question about authority. Galileo looked through a telescope and saw that the moon had mountains. He was told the moon was a perfect sphere. He believed his eyes. He was punished for it. This happens constantly in every era, in every domain. People observe things that contradict the official narrative. They see corruption that is supposed to not exist. They see systems failing that are supposed to work. They see injustices that are supposed to have been solved, and they are told they are wrong, that they are seeing things, that they are troublemakers. Galileo's story is about what happens when you insist on what you have seen. Sometimes you are vindicated, sometimes you are crushed, but the question remains, do you trust your observations or the authorities who tell you to disbelieve them? This is not to say observation is always right. Galileo was wrong about the tides. Observations can be mistaken, instruments can be flawed, interpretations can be biased. But the solution to bad observation is better observation, not deference to authority. Galileo's method says check again, measure more carefully, calculate more precisely, test the claim. Do not simply accept because someone in power said so. This is uncomfortable, it is destabilizing. It means nothing is settled. It means every belief is provisional, subject to revision if new evidence appears. It means we could be wrong about things we are certain of. Most people do not want to live with that level of uncertainty. They want answers, not questions. They want certainty, not provisional conclusions subject to future revision. But Galileo's legacy is the acceptance of uncertainty, not radical skepticism, not the claim that we can know nothing, but the acknowledgement that what we know tentatively based on the best evidence currently available, and that evidence can change. This is also a story about the cost of being right. Galileo was right about heliocentrism. He was right about the moons of Jupiter. He was right about the phases of Venus. He was right about the mathematics of falling bodies. And being right cost him his freedom, his health, his daughter, his peace. Being right is not enough. Truth does not defend itself. If you want truth to prevail, you have to fight for it. and fighting means navigating power, building alliances, understanding your opponents, avoiding traps. Galileo failed at that. He was politically naive. He made enemies unnecessarily. He underestimated how much the Church had invested in Aristotelian cosmology. He thought being right would be enough. It was not. This is a bitter lesson. We want to believe that truth wins out, that evidence speaks for itself, that reason prevails. But history does not support that. Truth wins when enough people with enough power decide to accept it. And that decision is shaped by politics, economics, social structures, personal relationships, accidents of timing. Galileo's truth won eventually, but not in his lifetime, not in time to save him, and only because others carried it forward, refined it, defended it, until it became too useful to ignore. What about the relationship between science and religion? Galileo's trial is often presented as the paradigmatic conflict between the two. Science seeks truth through observation. Religion seeks truth through revelation. They are incompatible, and Galileo's persecution proves it. But this narrative is false. Galileo was a devout Catholic. He wanted the Church to accept heliocentrism. He argued that Scripture and science were compatible, that both were divine revelations, that apparent conflicts arose from misinterpreting Scripture. Many church officials agreed with him. The problem was not science versus religion. The problem was that in 1633, the Church could not afford to appear weak, and Galileo's arguments implied the Church had been wrong. That was politically unacceptable. Moreover, many of the early scientists were deeply religious. Kepler was a devout Lutheran who believed his laws of planetary motion revealed the mind of God. Newton spent more time on theology than on physics. The idea that science and religion are inherently opposed is a later invention, a product of Enlightenment polemics and 19th century materialism. The real conflict is not between science and religion. It is between any system of established authority and new evidence that challenges that authority. It could be religious authority, political authority, academic authority, institutional authority. Whenever evidence threatens the foundations of a system, the system will fight back. Galileo was crushed not because he contradicted the Bible, but because he contradicted the authorities who used the Bible to justify their power. This happens outside religion just as much as within it. Scientists who challenge dominant paradigms face ostracism, denial of funding, rejection of their papers. Political dissidents who expose inconvenient truths face imprisonment, exile, assassination. Whistleblowers who reveal institutional corruption face harassment, prosecution, ruin. The mechanisms differ, the underlying dynamic is the same. Authority protects itself. Galileo's story, then, is not about science versus religion. It is about evidence versus authority. And that conflict is permanent. Finally, what do we do with the fact that Galileo was not a hero, that he was vain, arrogant, cruel to his family, obsessed with money and status, willing to compromise when it suited him, politically foolish, and wrong about several important things? We accept it. We accept that great achievements do not require great virtue. We accept that deeply flawed people can still change the world. We accept that genius does not make you good. This is important because the hagiographic version of Galileo, the saint of science martyred by ignorance, does not help us. It is a lie. And lies, even comforting ones, are corrosive. They make us think that only perfect people can discover truth, that only pure motives lead to progress, that only heroes matter. But history is not made by heroes. It is made by flawed, complicated, self-interested, brilliant, foolish, courageous, cowardly human beings who stumble forward, sometimes achieving something great despite themselves. Galileo was one of those. He saw farther than his contemporaries. He changed how we understand the cosmos. He helped create the modern world. And he was also a difficult man who hurt people close to him, who made enemies needlessly, who failed to see traps he should have avoided, who died broken and confined. Both of those things are true, And holding both of them in mind simultaneously is what it means to understand history. The question Galileo asked, the question he spent his life trying to answer, was this: if your eyes show you one thing and authority tells you another, which do you believe? He answered, believe your eyes. Check them, test them, refine your instruments, measure carefully, calculate precisely, but trust what you can see and what you can demonstrate. This answer cost him everything. It also changed the world. The question remains open. It remains open because authority does not go away. It adapts. It finds new forms. It uses new languages. But it still demands belief without evidence, obedience without question, acceptance without proof. And every time someone looks at the data and says, that's not what the model predicts, every time someone runs the experiment and says, that's not what the theory says should happen, every time someone checks the numbers and says something is wrong here, they are answering Galileo's question the way he answered it. They are saying, I believe what I can see, I believe what I can measure, I believe what I can prove. This is not the end of inquiry, it is the beginning. Because once you admit that observation can overturn authority, once you admit that evidence can change your mind, once you admit that you could be wrong, you open yourself to an infinite task. You have to keep checking. You have to keep testing. You have to keep asking questions. You can never stop. You can never be certain. You can never rest. This is exhausting. It is unsettling. It is frightening. It requires constant vigilance and intellectual humility. Most people refuse it. Most people choose the comfort of certainty, the security of authority, the peace of settled belief. Galileo chose otherwise. He chose the discomfort of questions. He chose the insecurity of evidence. He chose the unrest of perpetual inquiry. And he paid for it, and we inherited what he bought. That inheritance is not a set of facts. The specific discoveries Galileo made have been refined, extended, and in some cases corrected. The inheritance is a method, a stance, a way of being in the world. It is the stance that says, I will look, I will measure, I will calculate, and I will follow where the evidence leads, even if it contradicts what I have been told, even if it contradicts what I want to believe, even if it costs me. This is not easy. It was not easy for Galileo. It is not easy now, but it is the only way forward. Because the alternative is to believe what you are told because you are told it, and that way leads to stagnation, to error, to cruelty. It leads to worlds where questions are forbidden, where evidence is ignored, where power determines truth. Galileo refused that world. He insisted on a different one, a world where truth was discovered, not decreed, where understanding was earned, not inherited, where the book of nature was open to anyone who learned to read its language. He did not build that world alone. He did not even build it successfully in his own lifetime, but he pointed toward it. He showed it was possible. He demonstrated that authority could be challenged, that evidence could prevail, that human reason could grasp the structure of the cosmos, not perfectly, not without error, not without cost, but it could be done. And because he showed it could be done, others did it, and because others did it, the world transformed, and because the world transformed, we are here, now, still asking his question. We are the inheritors of his struggle, the beneficiaries of his courage, and the bearers of his responsibility to keep asking. If your eyes show you one thing and authority tells you another, which do you believe? Galileo answered with his life. He chose truth over safety, observation over doctrine, evidence over power, and he paid the price. What is your answer?